In this video, we show that generalized geography is PSPACE-Complete. Generalized geography originates from the game of geography where players take turns naming cities from around the world. The game starts with an arbitrary starting city and ends when a player is unable to continue. The game has two main rules. Each city must begin with the same letter that ended the previous city, and repetition is not allowed. We can visualize this game as a directed graph. The nodes of this graph are the cities of the world, and each edge A to B connects cities where the last letter of A is the first letter of B. The generalized version of the game, which we are calling generalized geography, is just an arbitrary directed graph without city names. To show p-space completeness, we first show that the problem generalized geography is in p-space. Let GG be defined as follows. Given a directed graph G and starting node N node, consider the following algorithm. Measure the arc degree of N node. If this degree is 0, then return reject. Construct a list of all nodes reachable from N node by one edge. Remove N node and all edges connected to it from G to form G1. For each node in the list, recursively call the algorithm with G1 and the node. If all of these calls return accept, return reject, otherwise return accept. This algorithm utilizes a recursive stack for its computation. Each level of recursion adds a single node to the stack, and there are at most n levels, where n is the number of nodes in G. Meaning that the space consumed by the recursion stack is polynomial and GG is in p-space. Now, to establish the p-space hardness of GG, we can reduce the formula game problem, which is known to be p-space hard, in polynomial time. An instance of the formula game problem consists of a quantified Boolean formula. The two players in the game alternate choosing values for successive variables of x. Player 1 wins the game if the formula ends up true, and player 2 wins if it ends up false. The formula is assumed to be in CNF form. For simplicity, we assume that the quantifier list starts and ends with the existential quantifier. However, this assumption does not affect the validity of the construction. We attempt the construction as follows. For each variable in the formula, we create a diamond structure. An arbitrary starting node is connected to the first variable. For each variable, we specify one node to indicate that the variable is false and the other to indicate that it is true. Each diamond structure is connected to the one for the next variable. This part of our graph will represent the assignments to the Boolean formula. We extend our construction by adding an extra node to the graph, connecting our variable structures to our clause nodes. Each of the clauses will then be connected to the literals in the clauses as specified by the Boolean formula. Finally, we will connect each literal to its corresponding node in the variable structure.
Now we'll have a look at the correctness of the reduction. So first we're going to assume that in the formula game, player 1 makes the first and the last assignment. So let's look at the graph constructed. Player 1 starts at B and then makes a choice based on the assignment that they would make in the formula game. If they were to choose true, they'd go left. If they were to choose false, they'd go right. Then the next two moves would ensure that player 2 gets the node where they would make the choice for the assignment on the next variable, and so on. Once all of the variables have been assigned, then player 1 would make the choice of going to C. After that, player 2 would have the choice to choose a node corresponding to one of the clauses, after which player 1 would have the choice to choose a literal in the clause. Now, if there were to exist a clause that was not satisfied, player 2 would have chosen that clause, and then player 1 would not have a literal that would have evaluated to 1. So any literal that player 1 would have chosen would have an edge from that literal to a node in the graph that was not visited. So player 1 would make a move, and the node that was not visited, then player 2 would make the move to that node, essentially giving player 2 the last move, and player 1 would lose the game. However, if all of the clauses were satisfied, then any of the clauses that player 2 would have chosen, player 1 would have a literal that would evaluate to 1, and then player 1 would choose that literal, which would lead to a node in the graph that was already visited. So then player 1 would have the last move, and thus resulting in player 1 win. Now we've shown that from how this reduction is valid by going from formula game to the general geography. We'll also show if in general geography player 1 was to have a winning strategy, how that would evaluate to player 1 having a winning strategy in the formula game from this graph. For that, we just have to take the route that would lead to player 1 winning in the general geography, and then we'd make the assignments based on that. So if player 1 was to take this route by going right, then we just assign false and so on to all the variables. This would essentially then lead to all the variables being assigned in such a way that at least one of the literals in the clauses was to result in a 1, thus making all of the clauses evaluate to true and making the overall formula evaluate to true. Now we'll have a look at the time complexity of the reduction. First, we're constructing a diamond structure with 4 nodes for each quantified variables. Thus, if there were m quantified variables, then the time complexity for this would be O of m. Next, for each clause and its literal, the corresponding nodes are created. So one for each clause and then one for each literal in the clause. So for a formula of length n, the time complexity would be O of n. And since each node has at most 3 outgoing edges, because this would be in CNF, so at most there would be 3 outgoing edges. The edge creation process is also bounded by O of m plus n, where m are the number of variables and n is the length of the formula. Thus, we have shown that the time complexity of the reduction is polynomial. So this is a valid polytime reduction. Since we have shown that this problem is p-space hard by showing a valid reduction of an already p-space complete problem, which is the formula game to general geography, and we've also shown that this problem is in p-space, we have shown that this is p-space complete.